So what it means is that we need to get something done to address the problem. When it comes to mortality, malaria alone is responsible for about 20% of deaths in children annually, of which 25% of these deaths were among children who are below 5 years. And based on this, I try to have the need to contribute my quota to addressing the problem. We all know about the SDGs 3.2, which is about neonatal and under 5 mortality, and the goal that is being set, where we want to reduce the neonatal mortality to at least 12 per 1,000 live births. And then under 5, we want to reduce it to as low as 25 per 1,000 live births. Then again, the SDG goal 3.3 talks about infectious diseases, and malaria happened to be one of them. And the goal is to end the epidemics of AIDS, tuberculosis, malaria, which I'm working on now, and the neglected tropical diseases, and combat hepatitis, waterborne disease, and other communicable disease by 2030. Now, we have seen the challenge as far as Ghana is concerned. It's a serious global public health problem, and Ghana is of no exception. And you all know for sure that in our part of the world, public health resources available to address health problems are so limited. What it means is that we need to develop ways where we can use the little we have optimally. And to do that, we try to develop processes that can help us to target those who are actually in need most than rolling out universal intervention. And in fact, in our part of the world, rolling out universal intervention is practically impossible because of the limited resources that we have. And sometimes too, you are very efficient when you're working on smaller things than when you're working on a bigger scale. So since we don't have the resource to address all the problems, and since trying to face all the problems at a goal, we might end up not achieving anything at all, it's better to target the little we have with those who need it most. And that is where the spatial component comes in. So here, what we try to do is to actually quantify the geographical variability in malaria transmission in Ghana, so that the little resource that the policymakers have, they can target areas where the risk seems to be high, and then we can make progress. And also, trying to do this, you need to focus on what we call more localized kind of spatial information, so that you can have a control over any intervention you want to roll out at those smaller scales, rather than addressing something at the bigger level, like a region or a whole country. So therefore, under this study, all I want to do is a very simple task for me, is to quantify more localized spatial variability of malaria transmission among underprivileged children in Ghana, and also taking into account time. Okay, so I'm looking at both space and time. Okay. Okay, so here there's a routine surveillance data in Ghana, which we call DIMS2. It's a national representative data, and other countries are also using the same. That district health information management systems. And this provides a robust and a very reliable data, which is based on routine surveillance. And normally it's aggregated at the district level every month, but because of the nature of the work we're going to do, aggregated the data to form a yearly kind of data rather than a monthly data. Very soon when you begin to see the maps, you understand why I have to aggregate at the yearly level, because dealing with 12 months per district, and there are 260 districts in Ghana, and from 2016 to 2021, that will be a lot of work. And most often, the idea is that if you have a very robust process, you could actually model at the monthly level, all right? But in generating the final output, you can aggregate at a year level and then do that. That one way or the other helps you to minimize some level of what we call masking of the real situations or only the real effects. But because of computational costs, I decided to get a yearly level, and that's what I've used in this study. So clearly, I've extracted the data on uncomplicated confirmed malaria cases for the 260 districts that we have in Ghana. That's what I've used. So from 2016 to 2021, we aggregated all the monthly data to a yearly data. Okay, so the outcome variable here of interest is actually number of malaria positive individuals per district, because the district is a rule of my analysis. And also, I just tried to demonstrate the capability of you incorporating some risk factors or covariate into your model. So here in the DHS data and the DIMS data, they have information on number of children under 5 per district, and also there's information about the number of male population or the number of female population under 5 per district. So to demonstrate the capability of also including covariate or maybe exponential variables, I will just take in these two. Where am I going? We'll get there when I am about to finish. Okay. So here, those who are not too mathematically inclined, don't worry too much. I will try to explain this in a simple term. So here, take the YIT to be the number of children who tested positive for malaria in district I at time period T or in year T. Okay, so that is total number of positive individuals per district in that particular year. So if it's 2016, then that will be 2016. If it's 2020, it's 2020. Okay. Then you also take the EIT to be the expected number of infected children under 5 years in each of the districts over a particular time. So this is what you observe, but what do you expect? The reason why that needs to be calculated is because we need that information to estimate what you call the risk or the standard serious ratio. We need that in our modeling. That's why we have to estimate that. Then you also have an item called NIT. The NIT here is simply the number of persons at risk at district I at time period T or in year T. Okay, so those are the parameters that I'll need to be able to generate the SIR and then the relative risk. So once that is done, because I'm not connected to this, so I cannot point for you, but it's fine. Once that is done, to get your expected number of malaria positive cases per district at time period T, all you need to do is to sum all the number of malaria cases across the entire study district, that is 260 districts, divided by the number of people at risk across all the districts. So that is giving you some kind of what we call a probability or some kind of incidence or prevalence. And if you do NP, it's simply the expected value, is that not it? Number of observations times the probability gives you what we call the expected value or the mean. So that's what I'm doing there at equation 1. Then based on that, I can move to equation 2, where I can divide the number of positive cases at district I at time period T or at year T by the expected number of positive cases at district I at time period T. That gives me what we call the SIR, which is similar to the relative risk that you want to estimate. So once that is done, all I need to do is to take the log of the relative risk. So when I take the log of the relative risk, that will be as a continuous function as you're seeing over there. But what we are saying is that the number of observed cases at district I at time period T, given the expected number of cases at district I at time period T, given our relative risk, actually follows a Poisson distribution with the parameters, the expected, and then the relative risk. So all I need to do now is to take the log of the relative risk, which will be on a continuous function, and you see that. So the beta 0 is simply your what you call the intercept. It doesn't depend on anything. But the X transpose IT beta, the X transpose IT is simply indexing a vector of covariate that I want to take into account in my model. And the beta is simply a vector of what? Regresses. And there's a coefficient, that's what we are seeing over there. Then the UI is simply what we call the structured spatial effects. So this is purely depending on the district that you find yourself. If district 1, that would be district 1. If district 2, that is district 2. So it's like a random effect that we are estimating based on the model. The VI is another thing linked to the spatial, but we call this one unstructured spatial effects. Or you can call it uncorrelated spatial effect, something like that. Then because we are taking into account also time, that's why you're seeing the gamma T over there. So that's actually quantifying the correlated temporal effect as far as the model is concerned. And the uncorrelated temporal effect is the one with phi T, the last one you're seeing over there. So these are all the parameters that I need to estimate in my model. And also, there's a need to have some assumptions around the parameter you're having, and this can be tested after fitting the model. So for when it comes to the intercept, the VI, the UI, all are assumed to be following the normal distribution, as you can see. And then we need, because this is implemented under the Bayesian framework, what it means is that we also need to assume some values, what you call the PRAL, because if you have the likelihood from the data multiplied by the PRAL, that gives you what you call the posterior distribution under the Bayesian framework. So that's what we are trying to do here. And so in literature, we don't have reliable PRALs from literature. So we use a VIC PRAL. That's why you're seeing those precisions like 0.005 and stuff following the gamma distribution. Okay, so those who are interested in this, I'll be giving another slide so you can go and read in detail the parameters I've just explained. You can go and read them. Okay, so we implemented the model under the integrated nested Laplacian approximation procedure, which is a very robust and a very good yielding stable result process, because what it does is that it combines both the analytical approximations and the numerical integration to form or to approximate the procedural distribution. And then to develop the interactive wave-based map, I use what we call the R leaflets, and I also generated another one that we call the graphic interchange format to improve visualization. So I wouldn't spend too much time on this. This is just to demonstrate for you that I've been able to take into account covariate despite the complexity of the model. Okay, so let's look at the spatial variation at the district level as far as the model is concerned. So here, this is the spatial effect, or what we call the spatial variability across the 260 districts in Ghana over the time frame that we are taking into account, that is from 2016 to 2021. Here, what you are seeing right now is a static map, but policymakers only can understand some of these things. So the critical aim of this modeling is to make visualization much easier for policymakers. So what I try to do, as you can see, it looks like there's some kind of changes from one time to another if you focus on certain particular districts. But that is currently not of interest to me. What is of interest to me is because I'm not seeing any numbers over there. I don't even know what the districts are here and there. So if I give this to a policymaker, it might not be too useful. They can see the hotspot, but who are they? Where are they coming from? So let's quickly try this, which is one of the reasons why I'm developing this. So I developed what you call a standalone application, also in R, where I can interactively engage with the output and put in a cursor, it will display the result for me. So that is my main aim here. There's a guy here or somebody here looking a bit red. So let's go and see who is there. Let me cancel this. So once I put a cursor, it gives me the relative risk at that location. It gives me the total number of children who were tested positive for malaria from that district. It gives me the district name. It gives me the SI value, it gives me the relative risk and the standard error. So even if a policymaker is not good at reading maps, just by putting your cursor, you get all this information. You don't need to struggle. If I move that to another location, it does the same thing. Let's go here. So you can see, it displays the name of the list, everything is there. So you don't need to struggle to ask yourself, I've provided ranges over there. It's okay. But sometimes policymakers want to know the exact value at that location, not the range of values. So those range of values are there, help you to determine where things belong, where they don't belong. But to get the exact values for each of the districts, you just have to put a cursor and all is there for you. Okay, so that is just that one. Because of time, you can play with the other one, similar process. You just double click. You don't need to pay any money to host this on the internet. It's a standalone app. I can email it to you. You can just open and you can examine everything you want to examine. The same process, as you can see. Nothing to worry about. So let me continue with the presentation. I feel like still this is not too good. So I decided to put all of them together, all the 6 maps together in one panel. So if I put the cursor, what I want to see is that wherever the cursor is, all the other corresponding locations will be circled in red, so that I can use my eye to just go through them and see whether the colors are changing or they are not changing. So that is the next one. Forgive me, I'm almost done after this one. I have just have some few, then I'm done. So this is going to load all the 6 panels together, also within the interactive web-based system. And all I need to do here is to put a cursor. Let's try the other guy. That is a Bono. What's the red one? That is Bongo. So you see the one I put a cursor on the Bongo district. All the other corresponding Bongo districts for the other years are showing in circle. So what I need to do is just to look at where I put the cursor and see the risk over there, I mean the color over there, and see if the color is the same across the other 5. You can tell clearly that the first one was more red than all the others. Okay? So that alone demonstrates the fact that the prevalence is not stable from time to time as far as the risk of malaria transmission is concerned. Okay. So that is it. You can play with it any way you want. So let me go back to the slide. Now, I also want a situation whereby policymakers don't want to be seeing all 6 maps together. They just want to see a single map like this, and the map will be changing by itself for them to know either the transmission is stable across the district over time or it's not stable. So as you can see, we're watching the top as well. The year is changing, and the colors keep changing. It's an indication that the transmission of malaria across districts in Ghana is not stable over time. There's some amount of variation, as you can see clearly. And that one is a graphic interchange format. And finally, I need to showcase that every work you do, there's always some level of uncertainty around it. So how do I quantify the uncertainty around those predictions? That's a relative risk. I use the standard error as a measure of uncertainty around that. Those who are interested, you can also use what we call the 95% credible interval to show that is still fine, but I prefer to use standard error in this case. So generally, you can see that the standard error is generally very low. The maximum I'm seeing here is about 0.04, very, very low. Okay. And even that one is only from 2016 and 2017. All the other years, the 0.03 to 0.04, you can see it on other years, meaning they even experience much lesser standard error. Okay. So on that note, if I've not confused you up to this stage, then some key findings, we realized that both the log number of children and that of number of males were associated with malaria transmission. Then the LoRa and then another district in the Upper West region recorded higher relative risk except in the year 2020. A majority of the districts and municipalities in the Savannah, Northern, and Bono East regions recorded a higher relative risk of malaria over the entire period. And our statistics are associated with the predicted relative risks are generally very low. Strengths. Because in the modeling, we take into account the neighboring effect of each district. So districts that have lower count, we can borrow information from districts with higher counts. So the issue of unstable predictions are minimized because you have a good number of count to deal with the neighboring matrices. So that is one good thing about this modeling process. Of course, I would love to have information from the data on geographically indexed malaria data. For instance, we talk about distance to nearest health facility, distance to water bodies, even the quality of data, how it is measured, all this, but these are not available in the data set, so I can't take care of that. But these are things we hope to explore if we get some finding. Okay. So as you can see, the geographical and temporal inequalities we found are serious threat to achieving the SDG 3.2 and 3.3. And also the finding from the present study provide a critical tool for malaria surveillance, elimination, and control strategies. And the findings can be used by both local, national, and global decision makers responsible for the health and survival of the children to better understand more localized district level patterns for under-5 malaria, and also to design more precise high-impact policies and intervention strategies that are aimed to reduce malaria burden and interstate mobility and mortality in the country. Of course, there's a need for further studies based on the limitations that I mentioned. Some few acknowledgements. Bill and Melinda Gates Foundation for funding my trip to this place. They have done well. We have also funded some of my projects earlier, so I'm very grateful to them. Gavi as well, and all the other ones as well. On that note, because of time, I'm happy to end here and to say a very big thank you to everybody for listening. Thank you.
Thank you so much. I think we'll take one question. Saw your hand first. Sorry, Michael. You'll have to find him at tea break.
Yeah, thank you for such a wonderful presentation. And more so for your, I like the graphic part of it, the user graphics. Can you go to question 3? You just have a question on question 3.
What?
Maybe we can go back a bit.
Is it page 3?
Equation 3.
Equation 3, okay.
Yeah. Just have a small question.
Yeah. We'll get there.
Yeah, thank you. Yeah, just next. Yeah. So actually, thank you so much again. But when you transition from question 3 to 4, I can see the E is missing. The how to call it, the expected rate. So I don't know, continue like this or what happened, because that case, your odds ratios or relative risk won't be standardized. I don't know.
Yeah, thank
Yeah.
you. That's a very smart one. And thanks for the question. So we use the expected value to do what we call the offset when you're fitting the model. So you will not see that here, but that will be during fitting of the model. We call it the offset. I don't know if you remember Poisson. If you take the offset, you use the expected value to do the offset. Okay, now I'm saying that, okay, let's look at this. Let's look at this. Thank you. Look at the EI here. The EI is a summation of that. We get expected from here, right? Now look at question 2. Did you see EIT in question 2? Okay, that's what we used to generate the relative risk, is that not it? So it's be taken care of. And we use that as an offset when you're fitting the model. Look at this. Sorry to close you guys. This guy is what you're taking the log of, is that not it? And how did he get a guy? There was a part of EIT already. So when we are fitting the model, we use just an offset, yes. YIT. YIT is already here. These two guys give us the relative risk. You can see me if you're not, if you're not okay. Yeah. Okay, thank you.
Great, thank you. I think in the interest of time, we'll finish up, but please find Justice at lunch if you need any other lessons in modeling.
Thank you.
Thank you.